Hello everybody, this is Jens Nickel from Elektor. We are now at the Segger booth and this is Dirk Ackermann. He knows everything about the most famous Segger products like the J-Link and the Embedded Studio and of course the MBOSS. Dirk, let's start with the Embedded Studio. You can say maybe something about the latest developments.
Okay. Just quickly about the Embedded Studio. Embedded Studio is a development environment for embedded systems. We support multiple targets like the RISC-V targets, the ARM targets, and it can be executed on different operating systems. So you can use your Mac computer or Linux-based computer or Windows-based computer.
How many microcontrollers are supported at the moment?
The thing is that we usually are quite generic about the support. So basically, any of the previously named CPU IP vendors are supported. So that's some. What we do is we have specific packages for each microcontroller to make it easier for the developer to start with everything. So we have some CPU packages there that someone can specify this microcontroller. But I don't have the exact number on top of my head, sorry.
Can you drop some names of platforms?
Of course. So we can talk about Ambic, we can talk about Sci5, Nuvoton, NXP, ST, Renesas. So basically all the big ones anyway. But we also support all the small ones. So there's a lot of newcomers in the market right now, and many of those approach us quite early and ask for we support them. And that's what we usually do in these cases.
And of course, the core is the compiler. Can you say something about this?
Actually, the compiler is part of the tool chain and the first part of the tool chain. Originally, we've just used GCC and LLVM and offered both on the same package, so people could choose which option they wanted to have. Today, we actually have our own compiler. We base it on the LLVM implementation and optimize a lot of the things that in the end we came up with our own compiler in the end, and it generates very, very small code. Has very good performance. So in total, with a complete tool chain, which we optimize in all parts, so we have our own linker there. We have our own runtime library, and the runtime library is mostly written in assembly code to get out the most of it. And when you get at the full tool chain, basically we generate a very, very, very small executable for the embedded system. So basically, we haven't seen anything getting smaller with the code that we use for that. So, for example, we use Embedded Studio to generate the code for the J-Link, and we are very happy with it. And our developers are very demanding, so that they work with Embedded Studio on their free will, not being forced upon. Say something about this tool chain, actually.
For the people who don't know Embedded Studio, can you say something about the license model behind it?
Yeah, that's a good question, because we have a model that's called Segger friendly licensing. During the show, someone said, "Oh, that's generous," so we considered to change the name a bit and say Segger generous licensing.
Okay.
Because what we do is basically we offer this software for download, no obstructions. The only thing is, if you don't have a license installed, you will get a notice that you're using this in a non-commercial, hobbyist, or evaluation environment. If you use it commercially, you require a license. And that's a pop-up that occurs once a day or so. So people who use it in a hobby project have no big obstacles, they can just use it. Okay. People in countries who want to train on this to get further can use this without needing to purchase anything. And yeah, so that's the licensing model behind it. So fairly straightforward. Think about the shareware in the 80s, 90s, similar to that.
Yep. Let's come to the next product. That's the MBOSS real-time operating system, and there's now a new version from November on, you said in the preparation. Can you say something about this, the MBOSS Ultra?
Of course, yeah. We use our own, as I mentioned with Embedded Studio, we use it to generate the code of J-Link. At the same time, we use our libraries like the RTOS, the USB stack, file system, network stack inside our hardware products as well. So naturally, we do that with MBOSS too. And at some point, we realized that the signal generation we have in J-Link for the debug interface, at some points we run into limitations where we could not generate the signal we actually wanted because there was some timing not in the exact spot where we required it, or we had some we could not use the performance at that moment which we wanted. And we tried to figure out what was interfering with it, and we actually found out that was a system tick.
Yes.
And finding the system tick as being a problem triggered some very interesting and, from our point of view, groundbreaking development, because what came out of it was a change in paradigm for the development of an RTOS. An RTOS without a system tick basically has no time base. At least it appears so, because traditional RTOS all have the system tick as a time base. And when you want to have, when you want to schedule between the ticks, you either have to pull or you have to modify the time base of the system tick. Modifying the time base of the system tick is a problem if you vary it. So you have to keep it fixed. If you vary it, you
get problems with the interfaces, for example.
And you lose your time base and stuff like that. And if you change the frequency on a fixed base, you run into another problem. If you go on to a higher frequency, you have a lot more system ticks that might interfere with your execution a lot more times. So you decrease the performance of your software, you increase the power consumption because of the increased number of system ticks and context changes, context switches. So that's actually a problem in those cases. And what we've done is basically try to figure out how to get rid of the system tick and still have the operating system fully functional. So what we now do is we base our timing on a cycle. So we have a complete cycle-based scheduling. And now we can say, okay, the next task is in X cycles or in X nanoseconds. Let's say 150 nanoseconds next task that needs to be executed. And the one after in 150 microseconds, stuff like that. So we can even mix it because we always can calculate down to the cycle in that case. And that makes us more precise on the execution. It automatically gives us a tickless mode. The traditional RTOS has to do some context switching to actually activate the tickless mode. Then the tickless mode sometimes needs to wake up because the sleep time cannot be made as long as you will require, and then you have to start it again, stuff like that. But the real benefit of MBOSS Ultra is actually in the precision. So when we have some hardware operation which usually has a fixed time, let's say we write to a non-flash memory, takes 30 microseconds in this example, then with MBOSS Ultra you basically trigger the hardware function and then delay for 30 microseconds. And that's all. When you have a traditional RTOS, you have two options. One option is you say, okay, I delay and continue working after the delay. But depending on where you are within the two system ticks, this might be a very long time until your system wakes up again and continues to operate. Yes, this is a real problem if you do signal generation, for example. And the solution to this is basically pull until this operation is ready. But even then, you won't with polling, you cannot you cannot do something else because you need to poll and vary the state. And as the polling does not necessarily hit the exact spot where the function is ready, you still be later than with a dedicated delay that you can set with SAMS Ultra. So so that's basically the part that we think is groundbreaking here. And the power consumption effect is actually a side effect, a very nice side effect. It's approximately 5 to 10%, but it's,
Of course, an operating system must be very small in a microcontroller. Is this much bigger than the usual MBOS? Is it comparable?
It's comparable.
Yeah.
It's approximately. I don't have the numbers in my head, but it's comparable in size, definitely.
Okay. Then we maybe can come to the third product. That's the MWin App Wizard, and it has something to do with touchscreens. So
actually, the App Wizard is an extension to our graphics library. So the graphics library we have enables developers to create the user interface. So what we have here is an example for an oven application. So you could, in this case, you could go directly to the operation and set different parameters, or choose a recipe for a cake, for example, and then start the program, stuff like that. So, and all this traditionally that requires a very high programming effort.
Yes.
And when we talk about user interfaces, there are a lot of specialists about user interfaces, but none of them can program.
Yes.
So the problem is now, how can we bring this specialist together with software? So we need a tool here, and that's the App Wizard. And the App Wizard is basically used to create the interface in a graphical way. So you set elements there, connect the elements by attributes. So you can say, okay, this element triggers event A or event B, and can connect all these things. So actually you can create a fully functional app within the App Wizard without writing a single line of code. And then
so I can compare it with other platforms where you can program GUIs for PC, for example.
Yes, it's a similar idea. Yeah, correct. And then when you're done, basically, and there's still something left that you could not model with the App Wizard. For example, you cannot read a sensor.
Yes.
With the App Wizard. Yeah, so you need some code to read the sensor. But then you basically generate the code from the App Wizard and load it into Embedded Studio or any other IDE. We have multiple options to connect to different IDEs. And then you can work in the IDE, change the code there, and read out the sensor and stuff like that. And then you're done with the hardware-specific part. Naturally, on the way, you want to control what's going on. So when you need to, when you create the interface, we have some sort of play mode where you simply say, okay, now show me how this is going to be in the application, and then the user interface designer can simply play with the interface, can see all the transitions on the PC, use them as if they were on actual hardware. The next step is actually the simulation, where you can download where you start Visual Studio to actually start a PC application. That PC application could, for example, already include some of the code you will later use in the target-specific code, which cannot be modeled with the App Wizard, and then you can actually see that code in operation as well. And then the third step is basically that you download it. That you load the project with Embedded Studio, download it directly to the hardware, and can play with it immediately on the actual hardware. So what we see here has basically not seen a single line of code written.
Yep.
So we've just been creating, we started the App Wizard, created the user interface. Actually, most of the part has been done by our graphics designer, not of our development team. And in the second step, our development team verified what he has done. And then they just triggered the embedded studio down and to download it to the hardware, and they were done.
How many boards are supported at the moment?
Basically any board. So MWin has a very generic driver interface that you can adapt with some configurations from the. So we have the driver addresses the LCD controller, and then there's a configuration that addresses the LCD.
I see.
And this two-step process enables us to support basically any driver, any LCD.
I see.
And we're agnostic of the microcontroller with MWin anyway.
Okay. Thanks very much, Dirk.
You're welcome.
Interesting news.